40?
No.
No, there was nobody who was age 40. I like it. All right. Were there a lot of people that were age 72?
Yes.
Yes. And the second most, peak, there's more around 72, but around 18, right? All right, good. So how would I have made this picture then? I would have went to Florida, or alternate universe Florida. And what would I have done?
Ask random people.
How old are you? Let me see your ID. No, I will figure out. Right. And then I would have started with a blank. As a, how old are you? I'm 2. Okay, 2. How old are you? I'm 97. Okay, 97. Right? And then slowly it would have built up into that. I really want you to understand what went into this. If I would have really done this, I didn't obviously go to alternate universe Florida, but if I would have, that's what I would have done to get here. All right, good. So it's a picture showing me how the individuals are distributed, their ages. All right, so everybody get me so far? Okay, so to go from here to what we really need in general, which is samples. What if I went to Florida, and instead of asking a person, how old are you, I took 20 people, and it said, get your average age and tell me what it is. And then I went and took another 20 people randomly. Get your average age and tell me what it is. All right, let me let that sink in. Is everybody understanding what's happening? You're like, yes, I understand, but I wish it wasn't. Too bad. All right. So, can somebody tell me an idea? What's going to happen to my picture when I go to make that picture? So this is individuals. I can say sample size is 1. And what's going to happen when I go to 20 people? What's the most likely thing to happen? Is it likely that I'll get a bunch of 92-year-old people? If I just randomly select people, and I just happen to get 20 92-year-old people, if I do, I'm like, where am I? Right? If I truly randomly do it, it should be all over Florida. It shouldn't just be around me. That would be convenience, and that would suck. I wouldn't do that. I know better than that. If I truly randomly select from all of Florida, it should be very unlikely to get a group of 20 92-year-olds. Does that make sense? So what's the most likely kind of thing that would happen? You're jumping the gun a little bit. Sorry. That's the correct answer, but too correct right now. What's going to happen? What kind of ages should I expect to get if I randomly select people?
You're going to get more of an average.
Sure, I'm going to get a mixture of ages, right? Maybe I'll get a few people from here and a few people from there. So my tallest peak should be at, and in fact, what do I expect to get? What's my expected value to get? 40. I love it. So any group, especially because I got 20, the larger the group is, the more likely it is that their average is going to be the average of everybody, right? Because if I take all of Florida at once, I'm going to get a line right on the average, because it's going to be the freaking average of Florida. Do you guys kind of follow? So if I take a larger sample, then it's going to be more and more closer to the mean. That's actually coming up in a minute. So if I take 20 people, the tallest peak should be at 40. Was there any individuals here? No. But now suddenly that's the tallest peak. Now what's the next most likely thing? Besides a mixture of these two groups, the next most likely thing would be like just a bunch of people around there, around this. Right? Do you guys get a feel for that? Yeah. So if it's not a mixture, then it must be people near the tallest peak of each one individually. So then maybe this picture would look like this. Those peaks corresponding to those. Let me stop there for a second. It's probably more like 10 would look like that, but oh well, it's too late for me. I already said 20. Because here's what kind of happens when you hit 30. Not 30 years old, but when you hit 30, what happens is that. That's really bad, but you see what I'm trying to do. It does become a normal curve, right? Above, around 30, it starts to become very close to normal. For almost any distribution. Almost anything you can imagine that you could draw, if you took samples of size 30 from it, it's going to come out to look like this. Now help me out. From here to here, who had a bigger standard deviation? And what's the standard deviation tell you? Careful. Yeah, I'm sorry. Go ahead. The distance from the mean, the average distance from the mean. So, on average, who was farther away from their mean? The first one or the second one? What's the mean? 40. Doesn't this have a lot of people right on the mean? All right, so again, let me try this again. The bigger standard deviation was the one that's further away from its mean on average, which of course will be this one, right? All right, so let me stop there. You guys see that? If the standard deviation is an average distance from the mean, and this guy's got a lot that are equal to the freaking mean, his average distance from the mean is going to be smaller than this one. So this one's got a bigger. So this sigma, I'm going to call it sigma 1, is bigger than sigma 2. And then if I take more people, what happens to the standard deviation? Gets smaller still. And how does that correspond to what we said? The larger the sample gets, the closer to the actual mean I expect that average to get, right? That's exactly what that's saying. So what happened to the mean as I took larger and larger samples? What happened to the mean? Stays the same. It's got to. There's an average age in here right now, right? There's an average age in here. Everybody has to agree because it's true. If I take 3 people at a time, do their averages, and then average all those together, am I going to get a different number? Please understand that I won't. If I take 1 person at a time versus 3 at a time, of course I'm going to get the same average. That's all this is saying. So the individuals had an average of 40. The 20 groups will have an average of 40. The 30 groups have an average of 40. The average doesn't change. The standard deviation gets smaller. I like it. All right, good. So that's the really high overarching concept behind this. Now let's drill down into what the formulas start to look like. All right? The formula for the mean is easy. In fact, this is mu. I call for this picture, this isn't mu anymore. This is mu sub x bar. Oh, shit. All that means is it's the mean of the sample means. Because again, what is this right there? What does that dot represent? A person who is over 72 years old, right? And I talked to them after I talked to these other people that were the same age. What does this dot represent? The average of 30 people. You guys kind of with me? The average of... No? Okay. So from here to here. So if I took 20 people at a time, what I'm going to plot... Here I plotted individuals I talked to. I'm going to ask, what's your average age? And they're going to say 40. And then I'm going to plot them. Yeah. So all the plotting I make, this is for individuals. This is for groups of size, whatever. I like it. So we got to create math. We already have the math that works for individuals. We've been using it. Now we got to see, how do I tweak things so that all the math we've done also will work for groups of size, whatever, size n. So n is going to show up in my equation somehow, because the bigger my sample gets, the smaller my standard deviation should get, for example, right? So the standard deviation formula has to have n in it somewhere. Okay, maybe. Okay. All right, let me see. What was I about to do? Oh, the formula for this guy is easy. Mu sub x bar equals mu, no matter what n is. You can't change the average just because you took 3 people at a time instead of 1. Or 20 people at a time instead of 1. You can't change. I don't want the average age to be what it is. Let me take 7 of you at a time. We'll all suddenly get younger. No, sorry. It's not the fountain of youth. Yes?
Oh, but there's an evacuation order for building 26 to 27 right now.
Really?
Yeah, we're not.
Oh, did you just get like a...
It says stay clear until call is given, so that might...
26 and 27. Good try. Yeah, we're in 36. We're like 10 numbers over from that building.
My brother's in that building. Oh, gotta save him.
I think your brother's outside of the building now, I think. I don't know what's going on. They didn't say what's going on? Just stay clear.
Stay clear of those buildings.
All right.
Scary.
Yeah.
Save us, Joe.
And the active shooter, I don't want to bring that up, but it sucks to have to do that. Faculty, we have to go through active shooter training. Right? Thankfully, we're not following the one politician's advice about have everybody throw shit at them. I don't know if you saw that. Well, because then they don't have to see us to kill. Anyway. That was good, Jeff. That was good. That was bleak. It's probably just power outage. So that's this. Now we got to figure out, well, what happens to this as my sample gets larger, right? Well, what's my new standard deviation going to be? All right, so in the vein of that, when it passes out, pay attention to the colorful side. This is coming up a little later on the other side. This is a specific example of the non-specific example I showed up there. So taking a distribution, taking samples from it to see what it looks like after you do that.
-2, but
Okay. So, to try to make sense of this, but just like on that sheet I gave out with where you flipped the coin 14 times, remember in the middle I had the histogram that looked normal? Getting a lot of vacant stares, so this guy. All right. Do you remember when I drew this, I made the width 1. You with me? When really these are specific, this is a discrete distribution, right? So, you do it. So, like 5, if I do this, can I get 4.8 heads? No, I can't. But I just made my bar that wide just so it looks more like a histogram, right? All right, so I can say, I can pretend like, in fact, later this is going to become a way that we do binomial probabilities using z-scores instead, is we pretend that 4 is 3.5 up to 4.5. So then it becomes continuous. All right, so that's something. So that's what I did here also. So obviously you can't get, if I put the number 1, 2, 3, 4 in a hat, I can't get 1.1. That would be a neat trick. I can't do that. But this just gives an idea of what it looks like. It's just uniform. I could just put lines there, but that's not very good visual. All right, I like it, maybe. So obviously if I put the numbers 1, 2, 3, 4 in a hat, I shake it and I say take 1 out, the probability of any of those numbers would be 1 out of 4. I love it. So they all have the same probability. So it's a uniform distribution to start with. Sort of like this was a 2-potato distribution to start with, I guess. We can call it that. So that's what the XP of X kind of table would look like, right? They each have a 25% chance of happening. So if you do all the work, you'll get the mean is 2.5. And the standard deviation would be 1.118 if you do all the work like what you should have done on the quiz, right? Hopefully you did. We'll find out. All right, let me stop there for a second. Is everybody with me? Now, what I've done here is just like I try to say about Florida. This is a little bit more easy to manage than a state the size of Florida. So I've got not a lot of things can happen. If I take samples of size 2, so out of that, I don't just pick one number, but I pick 2. What could I pick? And again, it's with replacement, so I'm going to put it back in. And why do I do it with replacement? So all the probabilities stay the same. Makes it easier math to work with. So what could I get? I could get 1 and then 1 again, and so forth. Right? So that's what these are. These are the actual samples of size 2 that I picked. Let me stop there. Because if you went to Florida, how many samples of size 20 could you pick? A lot. There's just a lot of people in Florida with me. So this is a little more easy to manage. I can actually just show you everything at once. And then I'm calculating the mean now for each of those. So I really want this to make sense. And this first picture in the table, the variable was a single number. Now my variable is going to be the average of two numbers that I picked. Just like here, this is a picture of individuals, whereas this is a picture of groups of size 30. They're averages. I like it. So if I do this, does everybody see where all this stuff came from? You guys agree with this? Because I do make mistakes. All right. I like you, John. We trust you, dude. It's fine. All right. What's the most likely thing? What's the thing that occurs the most? Which mean occurs the most? 2.5. That kind of makes sense because that is the mean. All right, that's the expected value, right? Okay. So if I take this data set now, this is now my data set. I do everything I did earlier, but I do it with this. So I put it into a chart, and does everybody see where this stuff came from?
Yeah.
How many 2.5s are there? 4 out of 16 total numbers, 16 total means. All right. This is not... this is painful if you really stop and think about it. I understand, but this is a weird concept, and this is my best attempt at a small enough grouping of things that we can try to get a handle on it. Florida is one thing. I want to really drill down and get to the numbers here. So what happened to the mean? If I do all the work again, if I do xp of x and I calculate the mean, I'm going to get 2.5 again. If you don't believe me, you can do L1, L2, L3, and then sum up L3, and it's going to be 2.5. Let me stop there for a second. All right. And if I do the standard deviation, I go some x squared p of x, that kind of thing, and do that, I'm going to get 0.791. Now, the standard deviation for this was 1.18. The standard deviation for groups of size 2 is 0.791. And if I divided those by each other, I would actually get the square root of 2. So they're off by a square root of 2. Let me just let you absorb that. So if I take what the standard deviation was for individuals and then divide it by the square root of 2, and what do you think 2 relates to? The sample size. I took 2 at a time. So if I did this whole thing again, but I did it with 3, I don't want to make ones because this would suddenly get much larger, right? But if I did it with 3, and I did this table for it, the standard deviation I get for it would be the old one divided by the square root of 3. All right. So the mean stays the same when I go from individuals to groups of size, whatever, but the standard deviation becomes the old standard deviation divided by the square root of n. That's the formula we have now. That's what the standard deviation, the new standard deviation is the old one divided by the square root of n. And I don't use the best language, and I just can't stop saying it because it's just, and you guys missed all of that shit, but I can't stop saying new and old. This is the standard deviation for individuals. This is the standard deviation for groups of size 2 in this case. All right. Maybe. So right now, all it is another formula. So let's try this out. Let's do a concrete problem using this idea. And this is what I love to do to you guys. I love to give you this kind of problem. Let's stick with this test average. Let's say that the average on some test was 74.3. And it had a standard deviation for the individual students. The standard deviation was 11.91. Now, in order for me to do this problem the way I want to right now, I have to tell you this is normally distributed. What I want you to realize, what came out of the earlier statements I made, do you guys understand? I don't have to say that if my sample size is more than 30. If I take a sample of size 37, I don't have to say anywhere that it's normally distributed because we know it is. We know that the new picture I make with all the means will be normally distributed because 30 is the magic number. And to be honest, what they did was they let a computer chunk on this population they fed it and said, computer, pick samples of size 11. And it did. And pick samples of size 12, and it did. And they saw at 30, no matter what no matter what it looked like, potatoes or uniform or triangle or whatever they fed into it, around 30, it became normal enough. Let me let that sink in. Now, of course, if it starts off normal, you don't need, you just feed in, and it's like, I got there after 1. I'm great. But if it didn't look very normal, maybe you have to go up to 10. The more uniform, the more symmetric and so forth, the less the sample. But you have to hit 30 to just cover everybody. So if I told you that I took a sample of size 37, I don't have to tell you it's normal for you to use the z-score chart. And it's greater than 30. It is normal enough. But I'll tell you it's normal, so I can do this. First question. If I pick one student. No, Jeff, it's a U. There you go. What's the probability that they scored less than 70? So they didn't pass. What's the probability a student didn't pass this test? That's old news. There's nothing new there. It's only new when I do what? Take a sample. There it is. Take a sample and I ask you about the sample mean. That's what tells you when you got to do this new stuff. Right? So to do this one, how do I draw this? Like that, Jeff. Okay, what do I put in the middle?
74.3.
Good, 74.3. I want less than 70. So what do I do to 70 so I can get that area? Find the z-score and then look it up. Good. So that's the standard z-score steps, right? In fact, sometimes, I don't know if this ever helps anybody, but you start with X score, you make it a z-score, and then you look up the area. That's your standard z-score problem. Maybe. So let's see. Z-score would be my data point minus the mean divided by standard deviation. And then whatever the hell that is. What time you got? Oh, it's just about time. Negative 0.37.
36.
All right. That's close. And then you look that up, like earlier. No, just one. Negative 0.3, 0, 1, 2, 3, 4, 5, 6 there. You guys get that? 0.3594?
Yes.
Put a count over right good. And that's my answer, because they want the area below. And that's what the chart tells me. So almost 36% of the students would have not passed. Ooh, that sucks. All right, so now here's the new stuff. Take a sample of an E of 19 students. What's the probability that their average score is less than 70? So before you do that, real quick, just one more example to explain things here. If I ask you to go out and randomly pick somebody, and you find somebody who's over 6 foot tall, that's not like crazy tall, right? Would you be freaked out? A little tiny, but not terribly. Like, all right, okay. If I ask you to go out and randomly select 20 people, and you really randomly select them, and they have an average height of 6 feet tall, how do you feel now? Now you should go, that would be a lot harder to do, wouldn't it? So that's a lower probability, because everything suddenly went closer to the average. That leaves very few people out here. So that's exactly what we're going to see here. If I take 19 students, their average should be close to 74.3. So there should be a lot less left out 70. So I got 36%. That was a lot. There should be a lot lower chance for 19 students to be less than 70. Because most of the averages should be close to this now. For groups of 19 students. So what's the very first thing I should do when I see this and I see this in the question, I change my standard deviation. I can't use this, because what's this good for? Individuals, I like it. But nobody said for nothing. Good. I need the one that works for groups of size 19, and how do I get that? You just kick ass. So you take, what was it, 11.91 divided by the square root of 19? 2 point. 730? 2.732?
Yeah.
Okay, thank you. Because remember, your weird stats teacher, he wants you to go out 3 places and stay. And now, here's the beautiful thing. This is what I said. Didn't it take me a long time to talk about freaking Florida and people and stuff and going around and talking how old you are, and they're slapping me saying, don't ask me how old. Doing all that didn't happen, but in my head it did. You guys, that took me it took me a while, and you guys did a really good job. You should get shirts for suffering through that. I don't have any for you, too bad. But I want you to realize what happens due to all that concept. The only thing that changes is you make a new standard deviation and then you do everything the same way. So on this step, instead of dividing by 11.91, I'm going to divide by 2.732. That's what I said earlier. A lot of concept, a lot of idea, and then the actual tweak is small. And you got a trigger to know when to do it. When I take a sample and I ask you about the sample mean, then you do this. So now I do the same thing. I do z is 70 minus 74.3 divided by this. Negative 1.57. So my picture, I can see, is like the same, really, right? Woo, it's a little bit skinnier, but who cares? Negative 1.57. So what area is below that? 1.57. 0, 1, 2, 3, 4, 5, 6. 0, 5, 8, 2. So before, what was probably an individual scored less than 70? About 36%. What's probably that 19 randomly selected people score less than 70? 5.8%, almost 6%. It went down by 30%. Because where'd everybody go? All the 19 people at a time, their average should be closer to the real average. At least very few stuff out here at the edges. So the actual picture would do this. Wow. They go closer to the mean. It pushes that up. Now this is a much smaller tail down there, right? Instead of 36%, it's only 6%. What was it? 0.0582. All right, so if you want to, you can look at the other side of this on your own time, but we'll do this Thursday. I'll actually have to I'll have a practice test for you on Thursday that you can put away until next Monday after spring break. I'll have the answer key on that Tuesday because that Thursday after spring break is the test. Holy shit. Holy shit, Jeff. It's on your homework sheet. Yeah. Not Tuesday. That's too evil for me. Thursday is just right. Just the right amount of evilness.